So, sir,
Yes.
I will.
Yesterday.
You can just welcome. Yeah.
Yes, sir. Good afternoon, everyone. Good afternoon, all of you, and wish you a warm welcome, all the participants. Yesterday, we have to in complete our today's complete our webinar. First topic on the basis of UV spectroscopy. What about these applications? Which are the instrumentation? What about these the spectroscopy? And all those parameters we have to study in yesterday's webinar. And today we have to continue on the basis of FTIR spectroscopy. And today is the second day of our webinar. And this webinar it also emphasizes on the basis of pharmacy regulation, PCI regulations as per BPharm course, on the basis of subject of instrumental methods of analysis. Its code is BP701. It's a final year subject. So it emphasizes these UV and FTIR, those type of instruments. So all those students, we have to get a benefit of this webinar also, and all those are you have to scope, and all those are objectives you have to study on these instruments. Today we have to go to our eminent speaker, Dr. Girijan sir. Yesterday I will introduce himself also, and he is also working as a product consultant in TOSHVIN Analytical. So you have to get a benefit for the how you have to work the FTIR, as well as how you have to analysis of drugs, on what you have to identify by the FTIR spectroscopy. So I will request to welcome sir from our institute, as well as from our principal Dr. H.Patil sir, as well as from our honorable chairman Dr. Tusharji Rande, and our secretary Mr. Nishanji Rande. So from this side, I will welcome. So now right now session for on the basis of FTIR spectroscopy. It's a theoretical as well as experimental knowledge you have to give our students as well as for the society. What about this? And because you have to go to directly on live, so you have to start your session, sir. Thank you, sir.
Thank you, sir, for the introduction, and welcome all the participants for the second day of the webinar. Yesterday, we had a very interesting topic, UV visible spectroscopy and its major applications. And today, we have another important and very interesting technique, infrared spectroscopy. So during these 2 hours time, I will be covering the basics of infrared spectroscopy. What is the difference between dispersive IR and Fourier transform IR? And what are some of the important accessories and what some of the important applications? I mean, this is what I'm going to cover in the limited time period of 2 hours. Okay, so I will start my session. Sir, I will share my screen, sir. Sir, you can see the slide, sir. Hello. 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 Sir, you can see the slide. Hello. So once again, I welcome you to this webinar on Fourier transform, infrared spectroscopy principles and applications. So what is infrared radiation? It's an electromagnetic wave with wavelength ranging from a lower limit of 0.76, approximately 0.8 micrometer, to an upper limit of 1 millimeter. Yesterday, we saw a part of electromagnetic spectrum, and infrared is also a member in this family of electromagnetic spectrum. and it is coming on the right hand side of UV. That simply means infrared has got lower energy content compared to UV radiation. The total IR radiation has got a range of 0.78 micrometer. Consider it as approximately 0.8 micrometer, and it is extending up to 1000 micrometer. So this is divided into three different parts. One is the NIR region, that is near infrared region. Then the middle portion, infrared region, and the last one is far IR region, or it's will call FIR region. So it is total ranges from 0.78 to 1000. So out of this total range, 0.78 micrometer to 2.5 micrometer is the NIR part. 2.5 micrometer to 25 micrometer is the mid-IR part, and 25 micrometer to 1000 micrometer is the far IR part. So when I am talking in terms of micrometer, I am talking in with respect to wavelength. Either you can talk in terms of wavelength or you can talk in terms of wave number. Wave number is centimeter raised to -1. We call it as inverse centimeter. Both are interconvertible. Either you talk in terms of wavelength or you talk in terms of wave number. But nowadays we are used to talking in terms of wave number rather than talking in terms of wavelength. So the total range 0.78 to 1000 micrometer in terms of wave number, it is from 12,800 inverse centimeter and coming down to 10 inverse centimeter. So if you look at the IR part, the middle part is called IR, or it is also called, sometimes people call it as MIR, mid-IR part, mid-infrared region. It has got a range in terms of wavelength 2.5 micrometer to 25 micrometer, or in terms of wave number, it is 4000 to 400 inverse centimeter. As far as an organic chemistry is concerned, an analytical chemistry is concerned, the pharmaceutical chemistry is concerned, the mid-IR portion is the most important part of the spectrum. That is from 4000 to 400 inverse centimeter. So most of the time, when you are getting a sample for recording the spectrum, IR spectrum, normally we record the spectrum from 4000 inverse centimeter to 400 inverse centimeter. Now, what is the utility? What is the importance of infrared spectroscopy? Yesterday, we had a lengthy discussion on UV. And I told you UV spectrophotometer or UV spectroscopy is predominantly a quantitative technique. And now you also know what is the reason why we cannot use UV as a qualitative identification technique. Because I told you an example, if I are getting two different compounds A and B, entirely two different chemical compounds A and B, and if you record the UV spectra of these two compounds, more or less these two spectra will be identical, very, very close to each other. That means you will not be able to differentiate compound A from compound B from the UV spectra. So that is the reason why you cannot use UV for qualitative identification. Many times you will not be able to differentiate compounds from the UV spectra. But at the same time, if you take a spectrum of compound A and compound B, these two spectra are going to be entirely different. That means from the IR spectrum, you will be able to differentiate compound A from compound B. And because of this, IR spectrum or IR spectroscopy has become a very, very important qualitative analytical technique. Even in pharmacopoeia also, as per pharmacopoeial requirements, in pharmaceutical industry, IR spectroscopy is one of the recommended identification techniques for pharmaceutical compounds. There are different identification techniques, but one of the recommended identification one of the recommended identification techniques for compounds or raw materials in pharmaceutical industry is by IR spectroscopy. It's a very important qualitative analytical technique. At the same time, you can also use IR spectroscopy for quantitative one. But many times people don't use it. Hardly 5% of the total customers will use IR spectroscopy for quantitative analysis. Whereas 95% or even more than 95% of the customers will be using IR spectroscopy as a qualitative identification technique. Now, this yesterday you saw the same slide, wave properties. When an electromagnetic radiation is actually propagating through a medium in the form of a transverse wave, it has got certain phenomena such as transmission, absorption, refraction, and reflection. All these things I think we have seen yesterday also. So some of the slides are common. This also you have seen yesterday. And the very fundamental equation C is equal to nu lambda, where C is the speed of light, lambda is the wavelength, and nu is the frequency. Okay, this we have already seen yesterday. And electronic transition also, we had a discussion yesterday when we were talking about UV spectroscopy. And in the case of UV spectroscopy, it is electronic transition that is taking place. Okay. So now a low energy radiation or a high energy radiation will be inducing two different types of transitions in the molecule. If high energy radiation is coming and falling on the sample like UV radiation, now you know it is an electronic transition that is happening in the sample. But at the same time, if a low energy radiation like IR radiation is coming and falling on the sample, a totally different type of transition is going to occur. So any low energy radiation, if a low energy radiation is coming and falling on the sample, you can expect two different types of transitions that are possible in a sample. One is called a vibrational transition and one is called a rotational transition. And when we discuss about IR spectroscopy, we are going to discuss only about vibrational transitions, because only vibrational transitions are studied by IR spectroscopy, whereas rotational transitions can be studied by microwave spectroscopy. So that we are not going into that. So we are going to discuss only about vibrational transitions that are going to occur in the sample when it is exposed to infrared radiation. So what is actually vibrating? When we say the vibrational transitions that are taking place in the sample molecule, but what is vibrating? The sample in the molecule, the molecular bonds are going to vibrate. Now, what type of vibrations are possible? How many types of vibrations are possible in the molecule? That is what we are going to see in this particular slide. Now, for discussing this slide, for explaining this slide, I am going to take an example of a methylene group. Everyone knows methylene group is a CH2 group. One carbon connected to two hydrogen atoms, CH2. There are two carbon hydrogen bonds, CH2. And then there are two more attachments that you forget about. So you consider only the CH2 part. This is a methylene group, carbon, hydrogen, hydrogen. Now, when we talk about vibrations or vibrational transitions that are taking place in the case of IR spectroscopy, these molecular bond vibrations are broadly divided into two types. One is called stretching vibration and the second one is called bending vibration. So first of all, let us see what is meant by stretching vibration. The very meaning of the word stretching gives you some idea. Stretching. Everyone knows what is meant by stretching. Suppose you get a very flexible rubber tube. You imagine you are having a very flexible rubber tube. And from both the ends, using your fingers, you try to pull the rubber tube. It's a flexible tube. You try to pull it. So what will happen when you are pulling? The length of the tube will increase. That means the tube is elongating. That means the length of the tube is increasing. When you are stretching it, when you are pulling it from both the ends, using both your hands, the total length of the tube is going to increase. That then we say the tube is elongated. Now you imagine you release your hand. What will happen? The tube will come back to the original position. Okay, everyone knows when you release your hand, the tube is going to come back to the original position. Now, the next step, what you do from both the ends, using your palm, you try to put pressure on the tube. You try to compress it. So when you're trying to push it from both the ends using your palms, what will happen? The tube gets compressed. And when the tube is undergoing compression, the length is going to decrease. Okay. So when you're pulling it, the length is going to increase. When you are compressing it or pushing it, pressing it, the length is going to decrease. And if you draw a perpendicular on this rubber tube while pushing or pulling, and if you draw a perpendicular on this rubber tube, there is a 90-degree angle. It is cutting a 90-degree angle on the tube. Whether it is elongating or whether it is compressing, the 90-degree angle is not going to change. It will remain exactly same. And this is what is happening in the case of a stretching vibration in the molecule. That means during the stretching vibration, either the bond length will increase or the bond length will decrease, but the bond angle is going to remain same. This is number you have to keep in mind. During stretching vibration, the bond angle is going to remain same, but the bond length is going to change. Either it is going to increase or it is going to decrease. Okay. So now this stretching vibration is divided into two types. One is called symmetric stretching and second one is called anti-symmetric stretching or asymmetric stretching. What is the difference between symmetric and anti-symmetric stretching? Now you look at the carbon-hydrogen bonds in the CS2 group on the left-hand side, top one. There is a central carbon atom. Two hydrogens are connected to the carbon. You can see the small blue spheres. They represent hydrogen. And so two hydrogens are connected to the carbon at the center. So there are two carbon-hydrogen bonds. Now you look at the arrow. Both arrows are pointing upwards. That means both hydrogens are trying to move away from the carbon. That means the bond length is going to increase simultaneously. Both the bond lengths, first carbon-hydrogen bond length and the second carbon-hydrogen bond length, both bond lengths will increase simultaneously. That is why we have put two arrows in the same direction, upward direction. That is one possibility. The second possibility, these two hydrogens can simultaneously come towards the carbon. That means both the bond lengths will decrease simultaneously. So whether it is increasing, whether it is decreasing, it is happening simultaneously in the same direction, and that is why it is known as a symmetric stretching vibration. Symmetric stretching vibration. Now below that we have shown anti-symmetric, and you look at the arrows now. The arrows are in opposite direction. When one hydrogen is trying to move away from the carbon, there is an upward arrow. The other hydrogen is trying to come closer to carbon. There is a downward arrow. So that means these movements are in opposite direction. One hydrogen is moving away and another hydrogen is coming closer to the carbon. So that means one bond length is increasing, another bond length is decreasing. That means they are acting in the opposite direction, and that is why we call it as anti-symmetric stretching. So you can expect in carbon, hydrogen, nitrogen type of bond, you can expect symmetric stretching as well as anti-symmetric stretching, and the absorption may be at two different locations also. So there are two symmetric and anti-symmetric stretching, two types of stretching. Now let us come to the bending side. In the case of bending vibration, exactly the opposite of stretching is going to happen. What is the fundamental rule in the case of stretching? Bond length is increasing or decreasing, the bond angle is going to remain same. Where in the case of bending, it is going to be exactly reversed. The bond angle is going to change, but the bond length is going to remain absolutely same. No increase in length or no decrease in length. But what is changing here is the bond angle. That's exactly opposite. What is happening in stretching and what is happening in bending, they're exactly opposite. In stretching, bond length, bond angle is same, but in the case of bending, bond angle is going to change. In stretching, the length of the bond length is going to change, but in bending, the bond length is going to remain same. Okay, so exactly opposite. Now this bending is divided into two types. One is called in-plane bending, and one is called out-of-plane bending. And you should understand what is meant by in-plane bending and what is meant by out-of-plane bending. So for the students to understand, I will just take a very simple example. You draw a circle, and everyone knows what the total degree of the circle is 360 degree. That's the total. We say it as 360 degrees. So you draw a circle on your board or on your paper, and try to cut the circle by putting a vertical line through the center, to the midpoint of the circle, the center of the circle. If you draw a vertical line, you will be dividing the circle into two equal hemispheres. Okay, that means it's a vertical cutting. You have cut the circle into two hemispheres vertically. One possibility. Second possibility, what I am going to do, I am going to draw a line again to the center, 100% horizontal line. Then also I am able to cut the circle into two hemispheres. But only thing, now I am cutting it horizontally. First time I cut it vertically, and second time I cut it horizontally. Now through this midpoint, I can draw any line at any angle and cut the circle. And each line is going to be a plane. It's a vertical plane, it's a horizontal plane, it's a slanting plane. And through 360 degrees through the midpoint, I can cut the circle by drawing a line at any angle. Only thing, the line is passing through the midpoint. So each line what I'm going to draw, which is passing to the center point of the circle, is a plane for me. Now you look, when you're sitting in the classroom in your college, when you go to the college, when you're sitting in the classroom and your professor is taking the class, there is a board on the wall where your teacher is going to write. The wall is actually hanging on the wall. It is a 100% vertical surface. It is a 100% vertical surface because the board is hanging on the wall, because your wall is vertical. Now you are sitting in front of a table. It's a flat surface table, and the table surface is a 100% horizontal plane. Now, if suppose in case if you people are sitting in front of a laptop, and when you're opening the laptop, I can keep the angle of the laptop at any, it need not be exactly at 90 degree. I can keep it at any angle. Each angle where my flap of the laptop is kept is an angle for me, is a plane for me. Okay. So when I say, now I am coming back to my bending discussion, in plane bending. Now again, our group is same, methylene group, CS2 group. Now I am going to keep this CS2 on the board. Imagine that you are sitting in the classroom, you are looking at the board, and I put the CS2 on the board. So carbon is on the board, both the hydrogens are also on the board. All the three atoms, carbon, hydrogen, and hydrogen, all are on the board, sitting on the board, which is a vertical plane. Now, in whatever way this bending is going to take place, there are going to be some movements of these atoms. But all these movements are happening, actually taking place on the board itself, on the same plane. Board is a vertical plane, you know that. Now, and these movements are going to happen. These movements are going to take place on the board itself. So that means it is called a in-plane bending. That means they are not going to a different plane. They are all on the vertical plane of the board. And those type of movements are called in-plane bending. Now the last one is out-of-plane bending. In-plane bending, I am going to again divide into two. But before that, I will tell you what is out-of-plane bending. In the case of out-of-plane bending, again, I am going to keep my CS2 group on the board. Carbon is on the board. One hydrogen is on the board. Second hydrogen is also on the board. But during the movement, certain moments during the bending process, some of the atom may remain on the board. That is your vertical plane. Some of the atoms may come out of the board, bend towards you, or bend to the back side of the board. That means they are going to a different plane. And that is why it is known as out-of-plane bending. Okay, so you understood the difference between in-plane bending and out-of-plane bending. In-plane bending means all the atoms, all the movements are happening on the same plane. So it is called in-plane. Whereas in the case of out-of-plane bending, some of the atoms may remain on the same board, but some of the atoms may come out and come to a different plane. That is called, it is out-of-plane. Now let us come to again in-plane bending. There are two types of in-plane bending. Probably you must have studied all this in your curriculum because Dr. Patil told me all these are there in your syllabus, so you must have already studied. And what we are doing is, what I am telling is not something very new, and only trying to refresh what you have already learned. That is only my intention. So in-plane bending is again divided into two types. One is called scissoring motion and one is called rocking motion. There are two types of in-plane bending, scissoring and rocking. And what is meant by scissoring? Everyone knows you all must be using a scissor at your home. Suppose if I want to cut a piece of paper, I want to cut a piece of cloth, I'll be using a scissor. So when you are using a scissor, what is the most, everyone knows how the scissor works. Scissor has got two arms. So when you are opening and cutting a paper or something, these arms will go apart and come together. They will move apart and come together. So the action will be like this. They are actually moving apart and coming together, moving apart like this, moving apart and coming together, and then it goes forward and making a cutting. Same way, in the case of a CS2, now you imagine the CS2 group as a scissor. Carbon is the central midpoint of the scissor, and one carbon hydrogen bond and the second carbon hydrogen bond, you assume they are the arms of the scissor. So how this scissor is working, they are coming together, moving apart, coming together, moving apart. So both the carbon hydrogen bonds will bend towards each other and then move apart, like the two arms of a scissor. But while doing this, they are all remaining on the same board. That is why it is called a in-plane scissoring bending motion. In-plane scissoring bending motion is one type. There is one more type called rocking. You must be knowing, you must have heard about rock dance. When two people are rock dance and two people are dancing, probably you must have seen some rock dance also. Two people are swinging in either direction, either to the left side or to the right side simultaneously. Both the people are bending either to the left hand side or to the right hand side simultaneously. So that is called a rocking motion. Similarly, in the case of our CS2 group, both the carbon hydrogen bonds can either swing to the left hand side or swing to the right hand side simultaneously. But while doing this, all the carbon and both the hydrogens are remaining on the same board. They are not going to a different plane. So it is called in-plane rocking bending vibration. So we have two different types of in-plane bending. One is scissoring and one is rocking. And now we are coming to the last two types, out of plane bending. Also, there are two different types. You must be knowing that one is called wagging and one is called twisting. And both are out of plane. That means some of the atoms are going to a different plane. Some of the atoms will remain on the plane of the board. Okay. Now imagine your CS2 is still on your board in the classroom. Carbon, hydrogen, all the three are on the board. Now twisting means what? Suppose you keep your two fingers straight and you can twist your fingers. When I am twisting my two fingers, which are held closely, I am keeping two fingers straight and I can twist the fingers. When I am twisting the fingers, one finger will it will bend forward and the second finger will bend backward. That means both are coming to two different planes. Initially, when both the fingers were held together, they were the same plane, it's the same vertical plane. But when I'm twisting my fingers, one finger is turning forward and one finger is turning backward. And that means both the fingers have gone to two different planes. Consider this as a CS2 now. So that means carbon, the central carbon atom is going to remain on the board. It will remain there. But one hydrogen is jumping from the board and turning towards you. You are all sitting in front of the board. So one carbon hydrogen bond is bending, coming out of the board and bending towards you. And another carbon hydrogen bond is going to the back side of the board, whereas carbon is still on the board. So this is called a twisting vibration. So hydrogens have come out of this board. It is called an out of plane twisting bending vibration. And the last one is called a wagging vibration. In the case of wagging, all the atoms are going to jump out of the plane. Either the carbon can bend towards you from the board and both the hydrogen can bend to the back side of the board, or it is vice versa. The hydrogens can bend towards you and carbon can bend towards the back side of the board. So that means all the three atoms are going to different planes. This is called out of plane wagging bending vibration. So in total, there are 6 possible vibrations that can happen in a molecule when it is subjected to IR radiation. 2 stretching vibrations and 4 bending vibrations. So what are those? Symmetric stretching, antisymmetric stretching, in-plane scissoring, in-plane rocking, out-of-plane wagging, and out-of-plane twisting. So total 6 different types of possible, different possible vibrations when a sample is subjected to IR radiation. And each type of vibration will be able to absorb. Many times it happens also. It can absorb at multiple position in the spectrum. That means when you are recording the spectrum from 4,000 inverse centimeter to 400 inverse centimeter, a certain type of vibration may absorb in multiple places also. That is the reason why your IR spectrum looks quite complex as compared to UV spectrum. UV spectrum, I hope all the students are familiar with the UV spectrum. It's a very simple, most of the time it's a very broad spectrum. Whereas if you look at an IR spectrum of a compound, of a sample, maybe a pharmaceutical drug, you will see multiple absorption bands are coming between 4,000 and 400 inverse centimeter. That means the spectrum looks quite complex. So the interpretation of the spectrum is also very important. So unless you have a basic, very good knowledge about from the first principles of IR, you may find it a little difficult to interpret the spectrum. But interpretation is not a rocket science. You can do that. Only thing you have to work towards that. You have to work for that. If you put a little effort, you take a personal interest, then definitely you can master the art of interpreting an IR spectrum. It's not a difficult issue at all. So now, for a sample to yesterday when we discussed about UV, I told you for a sample to absorb UV radiation, there has to be a chromophore. Unless and until a chromophore is present in the molecule, the sample will not absorb UV radiation. There are samples which do not have any chromophores. Those type of samples are called UV transparent samples because they will not absorb UV radiation at all. Similarly, for a sample to absorb IR radiation, there are two conditions to be fulfilled. Unless these two conditions are fulfilled by the sample will not be able to absorb IR radiation. So what is the first condition? When the molecule, that is your sample, is irradiated with an electromagnetic radiation, in this case our IR radiation, the vibrating bond will absorb energy if the frequencies of the light and the frequency of the vibration are identical. So please understand, in any molecule, these molecular bonds are always, even at normal conditions of temperature and pressure, these chemical bonds are always vibrating with a certain frequency. They're always vibrating with a certain frequency, and this is known as the fundamental vibrational frequency of the molecular bond. So depending upon the type of bond, these vibrational frequencies, fundamental vibrational frequencies can be different. Okay, so at normal conditions, all chemical bonds are vibrating with a certain frequency. It's known as fundamental vibrational frequency of the bond. Now, when this bond is subjected to, when this molecule is subjected to IR radiation, if the frequency of the incoming light and the frequency of the vibrating bonds are equal, there will be absorption of IR radiation. Otherwise, it will not be absorbed. So that is one condition for IR absorption. There is one more condition for the sample to absorb IR radiation. That's the second condition. A molecule must undergo a net change in the dipole moment as a consequence of vibrational or rotational motion in order to absorb infrared radiation. That means if a sample has to absorb IR radiation, there has to be a change in the dipole moment. You know what is the dipole moment, so I am not going into those details. You know what is the dipole moment and what is a dipole. You know, it's a charge separation dipole. So there has been a net change in the dipole moment, then only the sample will absorb IR radiation. If the dipole moment, change in dipole moment is zero, that means if it is a symmetrical molecule, then what happens, the sample, if there is a center of symmetry, then the dipole moment change will be zero and the sample will not absorb IR radiation. So that is why it is shown the intensity of an infrared band is proportional to the square of the change of the dipole moment during the vibration. d mu by dr square. Epsilon is proportional to d mu by dr square, where r is the internuclear distance. that is the distance between the two atoms, and mu is the dipole moment across the bond. So if d mu by dr becomes 0, that means you just recollect your Beer-Lambert's law. Yesterday, what we discussed. Capital A absorbance is proportional to what are the three terms you have studied. One is the molar absorptivity, epsilon, length of the path length, that is L, and concentration C. It is that absorbance is proportional to, is equal to, you can say is equal to epsilon multiplied by L multiplied by C, where epsilon is the molar absorptivity, L is the path length, C is the concentration. Now when this change in the dipole moment, your epsilon here, it is proportional to d mu by dr square. If d mu by dr, the change in the dipole moment is 0, that your epsilon will become 0. And if the epsilon becomes 0, absorbance will become 0. A will become 0. A is equal to 0. So that means there is absorption. So these two conditions are very important for a sample to absorb IR radiation. Otherwise, the sample will be IR transparent. Like a UV transparent sample, this will be an IR transparent sample. Okay. Now, when you record a spectrum from say 4,000 to 400 inverse centimeter, most of you must have seen the IR spectrum of many of your pharmaceutical compounds also. See, this spectrum can be divided into two parts. Right from 4,000 to 1,500, one part, and from 1,500 to 400, second part. The first part is known as the the functional group region, and the second part is known as the fingerprint region. Fingerprint region is the most important part in IR spectrum. Very complex region in the infrared spectrum below 1,500. So that means you have recorded the spectrum of a compound from say 4,000 inverse centimeter to 400 inverse. Now you are going to cut the spectrum at 1,500 inverse centimeter by drawing a line at 1,500 inverse centimeter. You are dividing the spectrum into two parts. The first part is from 4,000 to 1,500, which is normally known as the normally known as the functional group region. And the second part, that is from 1,500 up to 400 inverse centimeter, is known as the fingerprint region. Fingerprint region is the most important region. You get to know a lot of functional group information also, because you may not get many functional group information for the first part. Most of the time, you will find more number of absorption bands coming in the fingerprint region, whereas the number of bands coming in the first half will be very limited. They are all mainly because of stretching. So sometimes it is also known as the stretching region. And fingerprint region is known as the functional group region, because many of the functional groups also can be identified from the fingerprint region. More number of absorption bands will be observed. And most of these bands are mainly because of bending vibrations. Whereas the bands which are coming in the first half are mainly because of stretching vibrations. So that is why some people tend to call it as a stretching region also. Okay. So, and this fingerprint region is a characteristic of the molecule as a whole. So when you have two different compounds, A and B, maybe two different pharmaceutical drugs, when you record the spectrum of both the compounds, A and B, from 4,000 to 400 inverse centimeter, and if you look at the fingerprint region in both the spectra, A and B, you can find striking differences in these two. You will be able to see striking differences in the spectra A and B. And because of bending vibration region, the absorption bands that are appearing in the fingerprint region, there will be a lot of differences between these two spectra. And that is the reason why we are able to differentiate one compound from another compound by looking at IR spectrum, which was not possible in the case of UV spectrum. I mean, that is what we discussed yesterday. So this fingerprint region is characteristic of the molecule as a whole. So you can look at this. See, we have recorded the spectrum of a compound, say from 4,000 to 600 inverse centimeter. And we are dropping a line at 1,500 inverse centimeter, cutting the spectrum into two parts from 4000 to 1500. They are mainly the bands what you are going to see, they are all mainly because of stretching vibrations. We can see that nitrogen, hydrogen stretching, oxygen, hydrogen stretching, carbon, hydrogen stretching, carbon, oxygen, double bond stretching, carbon, carbon, double bond stretching. We can say so mainly because of stretching vibrations. And the fingerprinting region, what are the bands that you are going to observe mainly because of printing vibrations. So that is the most important region. I am not telling that the first part is not important. It's not like that. But the second part is more important compared to the first part. That's why it is known as a it's known as a fingerprinting region. Okay. Now here I have shown, for example, this particular slide has three columns. The first column, some of the important functional group, and one. By the way, I will ask a simple question to students: what is the utility? Where are you? What is the important information you are going to get from IR spectrum? Tomorrow, when I am going to give a chemical compound, and if you are recording the spectrum of that compound using an IR spectrophotometer, and you get an IR spectrum, what are the basic information you are going to get out of the spectrum? You are going to get information as to what are the possible functional groups present in the sample. Now, you know what is a functional group. Suppose if it is a carboxylic acid, COOH is the functional, it's a carboxylic acid functional group, COOH. Is an alcohol compound, you get an OH group, hydroxyl group, it's a functional group. If it's an amide, it is CONS2. If it is an amine, it is an NS2 group. So you have different functional groups, and these are the information you are going to get by looking at the IR spectrum. So in this slide, the first column is showing some of the functional groups. Second column is where is the absorption band going to come in the spectrum. Where is the absorption band appearing in the spectrum? And the third column is the intensity of the band. Many times the intensity of the bands also will vary widely. Some bands are very, very intense. Some bands are medium intensity. And for some bands, the intensity will be very small. So the intensity also can vary. That is also an important factor. You have to consider all the three. The position is important. The shape of the band is important. Intensity of the band is also very, very important. So there are some examples. For example, I'll just take one typical example of a functional group, C double bondo. C double bondo, what do you know? It is a carbonyl functional group. Carbonyl functional group, C double bondo. Now, if your sample contains a C double bondo functional group, you can expect a very, very intense peak somewhere between 1670 and 1780. 1670 inverse centimeter to 1780 inverse centimeter. The position, there is a range 1670 to 70 because the carbonyl functional group can come from different compounds. Like if you consider carboxylic acid COOH, that also contains C double bond. If you consider an amide CONS2, that also contains C double bond. If you consider a aldehyde compound CHO, that also will give a C double bond. If you have a pure ketone, benzophenone, I mean, it gets a pure ketonic group C double bond. Similarly, the C double bond can be contributed by different types of functional groups. So, depending upon the type of functional group that is contributing the C double bond, then the position can slightly vary. That's why we are always giving a band 1670 to 1780. But whatever the case, the intensity of the band is going to be very, very strong. It's a very strong, very intense band you can expect. And it's a very sharp band. Most of the time, it's a very sharp band. And that shows the presence of a C double bond or carbonyl functional group in your sample. So, I mean, you are getting an information. So, like that, you can find out what are the possible functional groups present in your sample by looking at the IR spectrum. Now, let us quickly compare what is the different dispersive and depth IR. But today, when we talk, dispersive IR is not available at all. Today, that is not available in the market. Once upon a time, only dispersive IR was available. FTR was not even developed. So when so quite some time back, long back, people are all working with dispersive IR. But now all the manufacturers who are manufacturing dispersive IR at that point of time, they changed over to FTIR, and today dispersive IR is not available. Only FTIR is available. It is only for you to understand what is the major difference between these two, dispersive IR and FTIR. In the case of dispersive IR, there are too many moving parts, mechanical parts. And since there are too many moving parts, there are a lot of wear and tear problem coming in the equipment. In the case of FTIR, it's a relatively simple optical system. So wear and tear problem is not there. Too many moving parts are not there. Not very complex optical system is not there. It's a very simple, relatively very simple optical system. Affected by dispersive IR is affected by stray light. And whereas in the case of FTIR, negligible stray light. Stray light means any unwanted light is called stray light. You suppose yesterday, I told you, suppose you want to have a measurement in your UV visible spectrophotometer for a certain sample at 254 nanometer wavelength. So that means you expect a monochromatic light having wavelength 254 nanometer only to pass through your sample and then subsequently go to the detector. That is what is required. But along with 254, suppose 250 nanometer is also coming, 260 nanometer is also coming. These are unwanted radiations. You don't want them, but they are coming somehow. And that is called a stray light. So any unwanted radiation is called a stray light. And if stray light is coming, your sensitivity of measurement will automatically decrease. Okay. So dispersive IR, that was a major problem affected by stray light. Whereas the case of FTIR, very, very negligible stray light. So that's not a major problem at all. Then lower signal to noise ratio and resolution in the case of dispersive IR. Signal to noise ratio, I hope you understand what is signal to noise ratio. Any electronic equipment, signal to noise ratio will define the sensitivity of the system. Signal and noise. Any electronic equipment, there will be noise production. Noise means not sound. Noise means basic disturbance. It can be because of inherent electronics. It can be because of very, very small variations in the incoming voltage supply. These are called disturbance in the base and they are called noise. So you cannot design an electronic equipment with zero noise. Some noise will be there, but the manufacturer will ensure that the noise is very bare minimum and signal is small. So if you take a ratio, signal divided by noise, signal to noise ratio, that's called S by N ratio, signal to noise ratio. If this ratio is very high, that means your sensitivity is very high. If signal to noise ratio is very poor, that means the sensitivity of equipment is very, very poor. Okay, so dispersive IR was having always a lower signal to noise ratio. That means its sensitivity was less. Whereas in the case of FTIR, we are getting excellent signal to noise ratio. That means you can have a very, very sensitive analysis. And similarly, resolution was very poor in the dispersive IR, but resolution is excellent in the case of FTIR. So you can see a lot of plus points, a lot of advantages for FTIR over dispersive IR. But one of the most important difference between these two is the next point. In the case of dispersive IR, single wavelength at a time. And FTIR, all wavelengths at a time. What does this mean? That means now again you imagine you have got a sample, you are going to record the spectrum from say 4000 to 400 inverse centimeter. Now, when it is starting at 4000 inverse centimeter, and finally it has to come to 400 inverse. That is the process called scanning. Now, when the sample is getting scanned, so when you are performing a scanning operation, the detector, there are so many wavelengths between 4000 and 400 inverse centimeter, and the detector will be able to look at only one wavelength. That means it will look at 4000 inverse centimeter, then it look at 3999, then it will look at 3998, 3997, 3996, like that. It has to one by one, it has to come to 400. So that means it was going to take quite some time. You can only see one wavelength at a time. And then it will go to the next wavelength. Then it will go to the next wavelength. So like that, it will look at individual wavelengths from 4000 to 400 inverse centimeter. What was the drawback? As a user, if you want to have a single scan of your sample in a dispersive IR, you will have to spend at least 10 to 12 minutes or even sometimes more than that. So a lot of time was consumed for even conducting a single scan of your sample. So that is because your detector is able to see only one wavelength at a time. And this is what is known as sequential scanning. Whereas in the case of FTIR, this is not happening. The detector is able to see all the wavelengths, right from 4000 to 400 inverse centimeter. The detector is able to see all the wavelengths simultaneously at a time. At a time, it can see everything together. And that is what is known as simultaneous scanning. That is the most important difference between a dispersive IR and FTIR. And as a FTIR user, what is your advantage? Your analysis time is getting shortened. When you are taking about 10 to 12 minutes or even more than that in a dispersive IR for getting a single scan, in the case of FTIR, in less than a minute's time, you can get multiple scans of the same sample. Sometimes you can get 36 scans, 45 scans, 64 scans, sometimes 100 scans of the sample. And the total time taken for all this will be approximately about a minute's time. So you can imagine what is the speed of analysis. Okay, and that's the most important difference between a dispersive IR and an FTIR. Okay. So IR spectroscopy instrumentation, dispersive infrared spectroscopy utilizes a diffraction grating for wavelength selection. Yesterday we had a discussion on diffraction grating, and that is a monochromator. And yesterday I told you what is the function of a monochromator. It is actually converting a polychromatic light into monochromatic light. So similarly, in the case of IR radiation also, IR lamp, it is giving out a polychromatic light. It contains different frequencies. They are to be separated because your detector will be able to see only one wavelength at a time. So all are to be separated. And for separating all these different wavelengths, you have to use a monochromator, and that is a diffraction rate. So here also we are going to use a diffraction rate in the case of your dispersive IR. Okay, but dispersive IR is, you people are all fortunate enough, dispersive IR is not available now. What is available in the market today is only an FTIR. And in the case of FTIR, there is no dispersion because you don't have to separate. You don't have to convert the polychromatic light into monochromatic light in FTIR. Because the same polychromatic light having all the wavelengths can go and directly fall on the detector, and the detector has the capability to look at all the wavelengths simultaneously. So that means there is no separation. So there is no conversion from polychromatic to monochromatic. So you don't require a diffraction grating. In the case of FTIR, no monochromator is there. But in place of a monochromator, we have something called a interferometer. That is the heart of the system. Interferometer is the heart of the FTIR. That is what we are going to see a little bit in detail now. What is an interferometer and how the interferometer works, and that is the very basics of your FTIR. Okay. So Fourier transform infrared spectroscopy uses an interferometer to replace the dispersive device and generate the interference beam that is then exposed to sample. So in the case of an FTIR, we are going to generate an interference beam. Two light beams are going to interact, interfere. Interference pattern is going to be produced. How it's going to be produced, that is what you should understand, and that's what I'm going to show you in some 2-3 slides. Okay. And this is just you don't worry about this. This is the dispersive IR optical diagram. Anyway, now this instrument is not available, so it looks very complex. You don't have to worry. And this is an FTIR optical diagram. And here also you will see a much better diagram. So I am just skipping this. Okay. Now there has to be a source in the instrument. Yesterday we learned about the sources in UV. Deuterium is there for UV light. Tungsten halogen is there for visible light. So similarly, in the case of infrared spectrophotometer also, there has to be a IR source. Okay. Now, infrared source consists of an inert solid which is heated electrically to a temperature approximately goes to around 2000 degrees centigrade, and then it starts emitting IR radiation. Okay. And there are different types of light sources, so we are not going to discuss all those. But one of the currently what we are providing in our equipments, what we are providing a source which is it's a ceramic source. It's a small ceramic bead that is used as an IR source in our equipment. There are other sources also available. Okay. Now see what are there are different types of interferometers in FTIR. At least three I am writing, I am naming three here. Michelson interferometer, Fabry-Perot interferometer, and SHIRPUR interferometer, which is also known as common path interferometer. Out of these, the most commonly used, the most popular interferometer is a Michelson interferometer. So we'll discuss only about Michelson interferometer. That is the one which is most widely used in FTIR, Michelson interferometer. So Michelson is the name of the scientist who has designed this interferometer. So that's why it is named after his name, Michelson interferometer. Okay. Now, what is a Michelson interferometer? It consists of two plane mirrors. There are two plane mirrors inside, and these plane mirrors are at right angles to each other. It is at 90 degrees. Two plane mirrors are placed at 90 degrees to each other, at right angles to each other. And then in between these two plane mirrors, there is a beam splitter. Okay, and the beam splitter reflects. And what is the? I think I will show. I'll go to a slide. Thereby, you will be able to understand this. See, I'll come back to this. This is basically this is very easy for you. It's very easy for you to understand. Michelson interferometer. You can look at the slide very carefully. You can see two mirrors. One is called a fixed mirror at the top, and on the left hand side you can see one is that is called a moving mirror, and both are kept at exactly 90 degrees, right angles to each other. Okay, they are plane mirrors, and one mirror is fixed, so that is why it's not a fixed mirror. It cannot move. That is permanently fixed there. And the second one on the left hand side can slightly move forward and backward to a very small distance. And so that means its position is not fixed. It can move forward and backward to a small distance. That is why it is known as a moving mirror. It is moving at a constant speed. Moving mirror. So one is a fixed mirror, one is a moving mirror. And in between these two at the center, you can see a beam splitter. And this beam splitter, basically, there are two potassium bromide pellets, two potassium bromide plates, KBR plates. And then you can see two different plates. And in between these two plates, you can see a very small, very thin, pink colored slice. You can see that's a germanium film. A very micron thickness germanium film is sandwiched between two potassium bromide plates, and that form the beam splitter. And what is the job of the beam splitter? And I use on the right hand side, you have a light source, IR source. Light will be coming out of the source, and it will come on the beam splitter. And the name of the material, beam splitter, then what it is going to split is going to split the incoming light. Whatever light is coming from the source will be split by the beam splitter into two equal halves. The beam is going to be split into two equal halves. One half will go to the fixed mirror, that is, and another half will come to the moving mirror. So one half, 150% of the incoming radiation is getting reflected from the beam splitter. It go to the fixed mirror. Remaining 50% of the incoming radiation will get transmitted to the beam splitter, and it will come to the moving mirror. Okay. So now the initially your fixed mirror and your moving mirror are at equal distance from the beam splitter. So when these two light beams are, one light beam is going to fixed mirror and another light beam is coming to moving mirror, they go and touch the mirror and they get reflected back because it's a mirror. So when the light is touching the mirror, it will get reflected back. So they will again come back. So during this process, they are traveling the same distance and they are traveling at the same speed. When they go and come back, both the light beams will again recombine. That is called a constructive interference of two light beams. So when the distance is same, two light beams are coming and meeting, joining together, recombining together, and that is a constructive interference pattern. Okay. And then this beam is passing through the sample compartment, and it will go and follow the detector. Now next instance, you imagine. Now when this process was taking place, your moving mirror and the fixed mirror were at equal distance. Now what happens? You imagine the moving mirror is slightly going back, is moving backward. Okay. So but fixed mirror is going to be at the same place. So whatever light is going to fixed mirror, it will get reflected back and come back to the beam splitter. And now the light beam that is getting transmitted to the beam splitter and coming to the moving mirror, now the moving mirror is slightly gone back. That means there is a larger path length. There is a difference in the path length now. That means the light beam has to travel an extra distance. And when it comes back, these two beams are not going to meet together. It is known as a destructive interference pattern. There will be a decrease in the intensity of light. Whenever there is a constructive interference of two light beams, there is going to be an intensity increase. And whenever there is a destructive interference of two light beams, there is going to be a decrease in intensity decrease. Okay, so and then this is so by moving the moving mirror through a small distance back and forth, we are able to create a path length difference. And because of the path length difference, there is going to be either a constructive interference or a destructive interference. And proportionally, there will be an increase in the intensity or decrease in intensity. Okay, so now I am going back to the previous slides. Okay, now just for your time, this is what the essence I've already told you. So instead of using a monochromator, the IR radiation after passing through the sample compartment can be analyzed using a Michelson interferometer. The interferometer consists of a fixed mirror, moving mirror, and a beam splitter. That is what you have already seen now. The radiation from the source is split into two equal parts. That also you have seen the slide. By the beam splitter, one half is reflected to the fixed mirror, while the other half is transmitted to the moving mirror. Here is the picture. After reflection, the two beams are recombined at the beam splitter. The two beams interact at any particular wavelength constructively or destructively, depending on the difference in the optical path. So that's what I told you now. Depending upon the distance through which the moving mirror is moving, there is going to be a difference in the optical. We are actually creating a difference in the optical path to produce an interference pattern. So depending upon the difference in the optical path, there will be multiple constructive interference and multiple destructive interference. Okay. So the intensity of the emerging radiation modulates in a sinusoidal manner. In the case of a broadband infrared source, the emerging beam is a complex mixture of modulation frequencies, which after passing through the sample compartment is focused on a detector. What does it mean? The intensity of the emerging radiation modulates in a sinusoidal manner. Sinusoidal manner means whenever there is a constructive interference, your intensity is going to increase. So it is like you consider it as a transverse wave. Yesterday we started with that. Suppose the radiation is passing through a medium in the form of a transverse wave. What will happen? There will be multiple maximum points and multiple minimum points. Okay, it's like a sinusoidal motion. That's called a sinusoidal motion. So here also, in the case of an interferometer also, depending upon the type of interference that is happening, whether it is a constructive interference or a destructive interference, there will be maximum points and minimum points, maximum intensity points and minimum intensity points. So that forms a sinusoidal manner. That's a sinusoidal curve that you are going to get. I mean, the intensities can be maximum whenever there is constructive interference. Intensities can be minimum whenever there is destructive interference. Okay. And that is what we are going to create. Okay. And then after passing through the sample compartment, this whole radiation is focused to the detector. Here we are not separating anything. That's a major difference you remember between your displaced layer and left layer. The detector signal is sampled at very precise intervals during the mirror scan. So during when the mirror is moving backward and forward to a small distance at a constant velocity, you are actually the detector signal is sampled at very precise intervals. Very precise interval. We are going to measure the detector output, the detector signal. The signal is measured at very precise intervals. Both the sampling rate, that is sampling rate means the measurement of detector output or detector signal at very specific intervals. That is called the sampling rate. The sampling rate and the mirror velocity, the velocity the mirror is moving, are very precisely controlled and measured by an internal independent reference. So there has to be a mechanism, there has to be a measurement mechanism, a controlling mechanism to monitor these two, the sampling rate as well as the mirror velocity. These two should be precisely controlled and measured by what? For that, we have a material, that we have a mechanism inside. It is nothing but a laser beam. We have a laser source inside, helium neon laser source is there. So we have a laser gun. Inside every FTIR, there will be a laser gun. And this laser gun is giving out a laser light, helium neon laser. And using this laser light, we are doing the sampling rate and mirror velocity. They are precisely controlled and measured. And that is why our laser light is used. And the resulting signal is called a interferogram. And for the interferogram, whatever you are getting, the result, the output is called an interferogram, which contains all the information required to reconstruct the spectrum using a mathematical process known as Fourier transformation. Fourier transformation is nothing but a very complex mathematical equations, mathematical transformation, a mathematical conversion. Because your interferogram, so what this is the interferogram what you are going to get. Okay, so this is the ultimately what you are going to get. This is interferogram. So the upper one shows multiple constructive and destructive interference pattern, and they are all added together. You will get an interferogram, and the interferogram is the detector output in an FTIR. Now, if you look at the interferogram, you will not be able to understand anything about the sample. Whatever sample you keep, A, B, C, D sample you keep, all these samples are going to give the same type of interferogram. You will not be able to differentiate one sample from another sample by simply looking at the interferogram, because interferogram is an output in the time domain. And the time domain output will be converted into frequency domain. Then only we will be able to understand that. So, interferogram is nothing but a set of data collected in the time domain, and this should be converted into a set of data in the frequency domain. Then we are able to understand that. We are able to understand what is our compound. We are able to understand what is the functional group. We are able to understand what is the absorption band, provided the data should be converted into frequency domain. So what FT is doing, so the conversion of your time domain data to frequency domain data is carried out by a mathematical equation which is known as Fourier transformation. So FT is a mathematical program. FT, Fourier transformation is a mathematical program wherein it converts the time domain data into frequency domain data. When FT is applied to IR, it becomes FTIR. When FT is applied to NMR, it becomes FT-NMR. When FT is applied to MS, it becomes MS data. So like FT can be applied to different techniques. It's a conversion mechanism. Time domain data getting converted into frequency domain data. So this we have already seen. So this is just to understand this FTR. We can look at this slide. There is a light source which is emitting IR radiation, is coming and falling on the beam splitter. The beam splitter is going to split it into two equal half. One half is going to fixed mirror, one half is going to moving mirror. When they are at equal distance, when they are coming back, they are going to meet each other, going to create a constructive interference pattern, passing through the sample compartment and going and falling on the and the detector is going to give a output, that is the interferogram. That is what is shown below that interferogram. And the computer program in your FT in your software, the Fourier transformation is taking place internally, and this interferogram is converted into a normal infrared spectrum. And once you get a normal infrared spectrum, you can understand that. You can interpret that. You will get information about your sample. Otherwise, looking at the interferogram, you will get nothing. Okay, so that is the basic principles of your FTR. And let us come to the basic components of FTR. You have a light source, IR source. You also have a laser gun, and you know the laser light. What is the responsibility of laser light? I've already told you. For the precise control and measurement of the sampling rate and the mirror velocity, moving mirror velocity. Okay, both are passing to the interferometer, and once they come out, laser beam is taken out and detected by a separate laser detector. There's a separate detector for laser. That's called a laser detector that is there inside. Only the IR light is going to pass through the sample compartment, and whatever is coming out of sample compartment, the entire light will go and fall on the detector, and the detector is going to give an output. As be processed by a processing unit is nothing but your software, and you get a output. So that is what actually, I mean, that's a very simple optical structure. And there are different types of detectors. We'll not be going into too much of detail because that will be too much of a lengthy hardware discussion. Types of infrared detectors, there are different types of detectors. Thermal detectors, once upon a time you were using thermocouples, but now thermocouples are not used because they are less sensitive. Then pyroelectric detector is there, photoconducting detector is there. These two are still used. We are using now both. Now most widely used detector is called a pyroelectric detector. And then there is photoconducting detector. Okay, so pyroelectric detector is the most important, most widely used detector in the FTR system. For thermocouple, I'm just skipping, and coming into pyroelectric detector, it's very, very widely used in the IR region. And then it is nothing but a crystal. A pyroelectric material is nothing but a crystal. Okay. And then IR radiation is a heat radiation. And when this radiation is coming and falling on the detector, which is a pyroelectric detector, which is nothing but a chemical crystal, there will be changes in the surface temperature. Okay, the change in the surface temperature results in a change in the charge. And the temperature difference, when it is getting heated up, the heat energy is getting converted into electrical energy. Okay, so that means it is getting converted into the heat energy is getting, because when IR radiation is coming, falling on the material, there is going to be an increase in the temperature. The surface charge will result, and the heat energy is getting converted into electrical energy by this material. So that is the function of the pyroelectric material. And what are the type of material that we are going? Normally TGS type of material, triglycine sulfate. Triglycine sulfate is a very good pyroelectric material, and that is what is used as a detector on IR. Now it is slightly modified nowadays. This TGS material was initially converted to all hydrogen atoms in this replaced by deuterium atoms. So TGS was initially converted to DTGS, deuterated triglycine sulfate, for a better sensitivity, deuterated triglycine sulfate. And then later on, this DTGS material, deuterated triglycine sulfate, is further modified by Shimadzu to prepare a material which is known as DLATGS, deuterated L-alanine coated triglycine sulfate. L-alanine is nothing but an amino acid. Why this coating was given on DTGS? Because every pyroelectric material has got a temperature which is known as Curie point temperature. Curie point temperature is that temperature above which the conversion efficiency, heat energy to electrical energy conversion efficiency will increase. So that's a cutoff temperature, 32 degrees, 32.1 or something like that, or DTGS. Now IR radiation is a heat radiation. Suppose your IR is working continuously morning to evening, your instrument is on, IR radiation is coming and falling on the detector continuously, the detector temperature is going to increase. By chance, if there is, by any probability, if there an increase in temperature and the temperature exceeds 32.1 degree, the sensitivity of the detector will decrease because it has already crossed your Curie point temperature. In that case, what will happen? The sensitivity will reduce. So to take care of this, to avoid such a situation, the DTGS material is given a coating of an amino acid which is L-alanine. So it has become L-deuterated L-alanine coated triglycine sulfate. By giving this coating, the Curie point temperature is increased from 32.1 degree to 61 degrees centigrade. So almost doubled. So now we are 100% sure that even if your instrument is going to remain on even 24 hours, this temperature will not be crossed. So that means at every point of time, the sensitivity of the instrument will be maximum. Okay, so and it has got, this material has got a very wide spectral range, right from 33,000 to 10 inverse the entire range. You can use this material as a detector. Okay. And what are the advantages of a pyroelectric detector? You get excellent signal to noise ratio. I told you signal to noise ratio is related to sensitivity. More the signal to noise ratio, more will be the sensitivity of measurement. So you get excellent signal to noise ratio, good frequency response, and the response is also very fast. You get a very, very fast response. Your measurement can be excellent. The speed of the measurement can be very good. Okay. Now, advantages of 50 IR. Multiplex advantage, aperture advantage, laser reference advantage, and application. Multiplex advantage, I've already told you what is by multiplex advantage. It's only a different name. Basically, what? In the case of dispersive IR, the detector has to see an individual wavelength from 4000 to 400. It can see only one wavelength at a time. So it has to come one by one by one, it has to come to 400. So that is taking too much of time. The same thing. That is what is on a multiplex advantage. But in the case of 50 IR, there is no dispersion. The entire radiation is coming and falling on the detector. The detector is able to see all the wavelengths at a time. And this is what is known as multiplex advantage. So that is what is written. Utilize. And as a user, your advantage is the speed of analysis. You can complete analysis in a very, very short period of time. It is very, very, the moment you keep the sample less than a minute, you can take multiple scans. I can take 64 scans. I can take sometimes 100 scans in a minute time. So it's so fast. So that's the multiplex advantage. And aperture advantage is better utilization of the quality of light. Means more amount of light as compared to a dispersive IR. More amount of light can go and falling on the fall on the detector. So more amount of light means more amount of light intensity is coming to a detector, and ultimately you'll get a much signal to noise ratio. That means your sensitivity is going to be again more. That's called an aperture advantage. Larger aperture size. Aperture means the opening, the window, the opening through which the light can pass through and fall on the detector. So here you have got a wider opening and more amount of light can come and it can fall on the detector. It can give a much better signal to noise ratio or results in improving light intensity and signal to noise ratio. Ultimately, as a user, you get a much better sensitivity. Then laser reference advantage, I've already told you what is the function of laser inside. The precise measurement and control of the signal detector sampling, the sampling rate as well as the movement of the moving mirror velocity. So they will be very precisely controlled and they have to be measured. And that for that reason, we are using a laser light, which is used as a internal reference light beam. Is used as an internal reference light beam. Okay. Then we have got application advantage. Once upon a time, when people are using dispersive IR, some of the samples were very difficult to be analyzed by IR. We are having a lot of restrictions. We are having a lot of disadvantages. And in the case of FTR, high sensitivity measurement, easy to measure even low transmittance sample. A sample which has got very low transmittance. It was very difficult to be analyzed by a dispersive IR, but today we can analyze those type of samples using an FTIR. Measurement of a very small area. For example, in pharmaceutical, suppose you are having a pharmaceutical tablet, and on the tablet you find a very, very minute microscopic black spot and you want to find out what it is, whether it's an external impurity or whether it is a part of the material. I mean, coming out of improper mixing in your formulation. You want to study what it is. At the same time, you don't even script such a very minute particle. But today we have a possibility to study those type of very, very, very small micrometer particles in a sample. Measurement of thin layer film on a surface, high speed measurement is possible, and you can today we have multi-layer packaging material for pharmaceutical packaging. The packaging material, there are multiple multi-layer packagings are coming. 2-layer, 3-layer, 4-layer packagings are coming. If you look at a packaging film, you may feel it is a single film. Maybe it is a mixture of 4 different types of polymer sheets compressed together and looks like a single sheet. And today, using an FTIR along with a microscope, you can find out how many polymer sheets are present in a single packaging material. It's a multi-layer packaging material. You can identify those polymeric material. You can identify, you can even measure the thickness of each layer. Those possibilities are using an FTIR and a microscope. And then very, very high wave number accuracy. So these are some of the major applications. So very difficult samples which were very difficult to be analyzed but dispersive IR. Today we have facility, we have accessories for all those type of samples, and all those type of difficult analysis are possible today using an FTIR. So you have lot of advantages, application advantages for FTIR. Now we are coming to some of the infrared window materials used to transmit infrared radiation. Window means it's a crystal. It is yesterday we know UV. You are keeping the sample in a cuvette. You are taking a solution, making a solution, and the solution is kept inside a cuvette. That's a sample holder. Similarly, in the IR also, when you record the spectrum, there has to be a sample holder. And the sample holder is known as a window material. And the window material is nothing but a chemical crystal. There are different types of crystals available. I mean, so when you're selecting a certain crystal, you have to keep in mind certain points. One is what is the wave number transmission range, from what wave number to what wave number you want to scan, because different crystals have got different ranges. Then chemical properties of sample is very important. Chemical properties of crystal is also very important. Physical properties of the material your sample is also important, and cost of the material. So these are some of the points you have to always keep in mind. Okay. See, there are different types of materials available which can be used as a sample holder, or which is known as a window material. Sodium chloride, potassium bromide, cesium bromide, calcium fluoride, silver chloride, germanium, then zinc selenide. There are different KRS5, even diamond, sapphire. Different materials can be used as a sample holder. Okay, so it's called a window material. And some of the window materials are highly hygroscopic water. So, for example, sodium chloride, potassium bromide, cesium iodide, these are all highly water soluble. So you should not use these type of window material for aqueous samples, because you will spoil the crystal. So if your sample is a water solution or a aqueous sample, or it contains large amount of water, then you have to use a window which is totally insoluble in water. You can use calcium fluoride. You can use zinc selenide. You can use KRS5. There are different windows where you can use aqueous solution. But windows like sodium chloride, potassium bromide, and cesium iodide, you have to be very careful, because they are a highly hygroscopic material, and you should never use an aqueous solution, aqueous sample along with this window material. Sodium chloride is a very not very expensive, but this window can be used only up to 600 inverse centimeter. 4,000 to 600 inverse centimeter you can use sodium chloride. Potassium bromide you can use from 4,000 to 400 inverse centimeter. Then there is another window which is an excellent window called KRS5, which is a 1:1 mixture of thallium bromide and thallium iodide. And this can be used up to 215 centimeters. So it's an excellent window, totally insoluble in water. So you can use an aqueous solution or a non-aqueous solution, not an issue. Only you should avoid aqueous solutions of very high pH. Anything above pH value 10, you should not use. And similarly, solutions of phosphates. you should not use. That is only restriction. Otherwise, it is an excellent window for both aqueous as well as non-aqueous samples. But cost-wise, it is slightly more expensive than other windows. Beer Lambert, so yesterday we have seen Beer Lambert. So here also IR can be used even for quantitative analysis. But if you look over to industry, see, not even 5% of the customers will be using IR for quantification. Majority of the people will be using it only as a qualitative identification technique, even though IR also has got quantitation capability. And if you are going to use IR as a quantitative analytical technique, then it has to obey Beer Lambert, so which yesterday we had discussed. Okay. What are the types of samples and suitable techniques? If you are getting a solid sample, suppose you are getting pharmaceutical powder or any solid material, there are different methods for recording the spectrum. NUJOL mulling, potassium bromide pelletization, DRS method, ATR method, and AEM method. And NUJOL mulling is nothing but this is basically meant for a solid material which is sticky material, sticky or pasty like waxy type of material, which is actually stick to something. So that is what is known as a waxy or pasty type of sticky material. For those type of material, what you have to do, you have to take a small amount of the sample, put 1 or 2 drops of NUJOL. NUJOL is nothing but spectroscopy grade liquid paraffin. It is water white. It's liquid paraffin. It's a saturated hydrocarbon. It is a viscous liquid, 100% transparent liquid. 1 or 2 drops of NUJOL you can put, and you can make a paste. And that paste is known as mud. And then you can take a fine drop of the mud on a KBR or a sodium chloride or a zinc selenide, any window material, and then just spread it on that, and then you can record the spectrum. So that's called a mulling technique. So mulling technique is used only for these type of materials. I mean, which are very sticky material. Suppose a wax type of material, those type of, otherwise no. KBR pelletization was also a very, very important technique till recently, especially in pharmaceutical industry. Pharmacopoeias were recommending KBR pelletization method till the recent time, but now there are other accessories available. KBR pelletization means you take about 1 to 2 milligram or 2 to maximum 2 to 3 milligram of your sample, and then you have to mix with 100 milligram of pure dry spectroscopy grade potassium bromide, and just mix it in a small pestle and mortar. Using a pestle and mortar, you can mix it well, and then this mixture is to be put in a die, and die is to be connected to a vacuum pump, and then you have to apply a lot of pressure, normally about to the tune of 10 atmosphere pressure we apply, and then we keep it for about 10 to 15 minutes time. And after that period, we release the vacuum, release the pressure, open the die, and if it is properly prepared, you get a 13 millimeter circular disc which looks like a piece of glass. That's called a potassium bromide pellet, which contains about 2 milligram of your sample and about 100 milligrams of your potassium bromide. That is how it mixes. We are mixing in this ratio and then making the pellet. And then you can keep it in a sample holder and record the spectrum. So KBR is here acting as a diluent. Especially when we are discussing about UV, every sample is to be diluted with a suitable solvent in UV. Similarly, here in the case of a solid sample, you have to dilute with potassium bromide. So potassium bromide is acting as a diluent. That is called a potassium bromide pelletization method. But then problem is potassium bromide pelletization method is a difficult method. First of all, it is time consuming, and from person to person, there can be a lot of differences in the pellet, quality of pellet. So that is a major problem. But recently, I think if you look at USP 34 and introduced 2 different accessories, DRS and ATR. And now in pharmaceutical industry also, you can use these accessories for recording the spectrum instead of going for a potassium bromide pelletization method. Potassium bromide pelletization method is a difficult process, subjective process. Lot of subject to person variations can be there in the quality of the pellet, which will be reflected in the quality of the spectrum. Instead of that, nowadays, now we have certain accessories which are very easy. It is not a subjective method. Quality of the spectrum will remain same, whoever is going to utilize it. So these are DRS and ATR. We are going to see that now. And then the last one is AIM. AIM is a microscope. A microscope can be connected to an FTR. Then it becomes a FTR microscope combination. Then if you have liquid samples, demountable cell, fixed path length cell, and you can also use an ATR. You can analyze gas samples also. In the case of IR, you can analyze solid, liquid, and gas. If it's a gas sample, you have specific gas cells available. You have to fill the gas cell with the required the gas and close it, and you have to keep it in the sample compartment, and you can record the spectrum of the gaseous material. And you can suppose you got a reflecting surface. You had a coating on a glass, coating on a mirror, or even coating on a metallic surface. You can use an attachment known as specular reflectance attachment. You'll see that now. And plastic containers and drums. Suppose you have got a huge 1,000-liter drum, which is put on your terrace, water storage, syntax tank, and the tank is getting continuously exposed to sunlight. Ultimately, the syntax is nothing but a polymeric material. So, because of sunlight, there are UV radiation coming and falling on the material, can undergo even oxidation. So, there will be a lot of changes in the material, and depending upon the composition and the formulation of the polymer. And if you want to study whether it has undergone some degradation, there is a material, that's a small accessory called SIC accessory. Of course, not of interest to pharmaceutical people. It's known as SIC, silicon carbide accessory that can be used along with an FTA. Then multi-layer packaging material. I told you now, multi-layer packaging material for pharmaceutical industry and consumer products. One a single layer, double layer, 3-layer, 4-layer layers of packaging materials are coming. So they can be actually analyzed, identified, and even the thickness of each layer can be quantified and measured using. But only thing, you require a microscope along with a FTR. Okay. Now we will see some important accessories which are relevant to even your out of these. Attenuated total reflectance and diffuse reflectance will be of very importance to you as pharmaceutical people. The specular reflectance may not be of much use to you. That's what I feel. So let us, and then infrared microscopy also. Infrared microscopy also got a lot of applications in pharmaceutical industry. So let us see what is attenuated total reflectance, that is known as ATR technique, attenuated total reflectance technique. And there are two different types. One is a horizontal type, one is a vertical. So horizontal ATR and vertical ATR. Again, for horizontal ATR is more popular, vertical ATR is not much. Okay, horizontal ATR is more versatile. It can analyze various types of samples. So what are the features of horizontal ATR? Sample pre-treatment is not necessary. Keep the sample as it is. You got a powder, you got a pharmaceutical powder, is a drug API. Directly keep the powder on the attachment on. There is a 10 centimeter crystal in the ATR, and you spread your powder on the crystal and just record the spectrum, and after that you take the sample back. There is absolutely no sample pre-treatment, sample preparation, nothing. Non-destructive analysis. After the analysis, you can take the sample back. Information on sample surface and ATR. Once you do the analysis using an ATR accessory, there is a mathematical correction that is carried out. That is known as ATR correction, which is to be done to the software. That's a part of the software. And what type of samples can be measured by horizontal ATR? Liquid samples, gel samples, solid samples like paper, cloth, yarn, API, pharmaceutical API, packaging material, and even lotions. So there are a lot of different types of samples that can be analyzed by horizontal ATR. That is why it has become more popular. Okay. Now, this is how it happens. You have a 10 centimeter crystal. What you see, the blue colored material, that's a crystal. There are different crystals that you can use. Zinc selenide you can use, germanium you can use. There are different crystals available. And your sample is kept on the crystal. And it has to be in close contact with the prism. The prism means the crystal. There should not be any air gap between a sample, and the sample should be in close contact with the crystal. And then IR radiation will come into the crystal for the source. It will undergo multiple times. It will undergo reflection from the crystal to the sample, back to the crystal, again to the sample, back to the crystal. multiple times it will undergo reflection. It is known as multiple internal reflection, or it is known as MIR, multiple internal reflection. The multiple internal reflection is carried out so as to increase the sensitivity of analysis. And finally, the radiation will come out, the light beam will come out, and it will go to the detector, and then you can. So that is what is, when it is penetrating the sample, it is actually penetrating to a very, very small depth, hardly in terms of around 2.5 micron or less than 3 micron. That's what it goes inside. Okay, so that is what is known as the penetration. It is called TP, penetration depth. Okay, now once the analysis is over, you can take the sample back. It is totally non-destructive, no sample preparation, no pre-treatment, and through the software to apply a correction, which is known as an APR correction. That's a part of software, standard feature software, and then you will get a proper spectrum of the sample. Very easy. Okay, whether anybody does this from person to person, there will be absolutely no variation in the quality of spectrum. Now, this is using an HATR. We have compared two different beverages, food industry, beverage A and beverage B. Look at the spectrum, very clearly shows two different spectra for beverage A and beverage B. Suppose you had recorded the spectrum on a UV spectrometer, both the samples A and B would have given you more or less identical UV spectrum. You will not be able to differentiate which one is A and which one is B, and what is A and what is B. Here you can see the striking differences in the absorption bands in the beverage A and beverage B. There are 2 or 3 separate bands, absorption bands are appearing in beverage A, which are not present in beverage B. And you can see the difference. Clearly, there are a lot of different the spectrum. So that means both the spectra are totally different. So you are able to differentiate between these two. And these are recorded by HATR without any sample preparation, just keeping the sample on the crystal and recording the spectrum, as easy as that. Okay, this is actually a cold cream and also a cosmetic material. Cold cream, cold lotion, especially when you're having, especially winter time when you're having a lot of dry skin, you apply a lot of hand lotion, cold lotion, so that your hand and face and all will be moist and will be very soft. So there are a lot of lotions available in the market, different brands, different makes, and different prices. And if you really want to find out which one is a better lotion, then you can actually use a FTR along the HATR. This is an evaluation of two different cold lotions that Shimatsu lab in Japan. And simply by pressing your thumb finger on the HATR crystal, they recorded the different, one is an untreated palm, second one is palm wiped with ethanol, and the last one is palm after applying a milky lotion. And then to study the differences, you require separate software also, which is known as a peak switch software is required. And applying the software, you will get certain information. A lotion which has got a better amide to water ratio is always a better lotion. It has got lot of moisturizing action. So here, milky lotion A is found to be having amide to water ratio 0.68 compared to milky lotion B, which is having only 0.43. The ratio is smaller in the case of B compared to, so milky lotion A is supposed to be a much better, more effective lotion as compared to lotion B. So you can actually evaluate. This is a typical cosmetic application. Vertical variable angle APR, I told you, is not very popular. This can be used only for sample has to stand in the vertical position. There is a crystal here also, and the crystal is standing in the vertical position. In horizontal APR, you have seen that the crystal is lying in the horizontal position. That is why we are able to keep liquid on that, powder on that, any other material on that. But here, the crystal is standing in a vertical position. So sample also has to stand vertical position. So that because of that, you cannot use a liquid sample, you cannot use a powder sample. But this accessory is utilized mostly in polymer industry tire industry, cable industry, packaging film industry, where a sample can be cut and kept in the vertical position along with the crystal. That is so because of that, it is not very popular accessory. Okay. Now ATR and now the refractive index of the prism is also important. You are actually selecting the prism, the crystal in ATR, that you have to be very careful because sometimes, suppose a sample containing carbon black, any black colored sample which contains carbon black, the theory is your refractive index of the crystal should be more than the refractive index of the sample. Otherwise, the quality of spectrum will be very, very bad, very, very bad. Now, here we have used a acrylonitrile butadiene rubber containing carbon black as a reinforcement. We record the spectrum on an ATI using KRS paper. But carbon black has got a very high refractive index, somewhere around 3.5 or 3.6. And KRS5 also has got a refractive index. I think it is less than that or slightly, almost very close to that. There is not a major difference between these two. So look at the spectrum. It's a very bad quality spectrum we are getting using KRS5. But if you use a germanium prism, germanium is the only crystal which is having a refractive index approximately 4.2 or something, which is more than carbon black. So any sample containing carbon black or black material, you have to always use only a germanium prism. Then only you'll get a quality spectrum. Okay. Then we also have a diamond spectrum. It is something like this, very hard samples, a polymer film or something, a polymer bead or something. Very hard sample when you are keeping, you can use a diamond spectrum, a diamond ATR. Here the yellow part, what you see is that's called the primary crystal. It can be KRS5, it can be zinc selenide. And over that, you can see a light blue color part. That's a pure diamond we are keeping. We are keeping a very pure diamond, a sapphire. And everyone knows diamond is a very hard material. And over the diamond, we are keeping our sample, which is a very, very hard sample. Then we are applying pressure with a mechanism to make the sample flat. And then it is a single, a single beam that you can see the beam is going, passing through the diamond, going to the sample, coming out, that's all. It's a diamond, and you can get a, it's a single bond set. It's called a single bond set here. You can get a single bond set here with diamond. You can also get a single bond ATR without diamond. When it is with diamond, the cost is going to be more. But for very, very hard samples, it's always better to go for a diamond ATR. Okay. This is a caffeine powder on a diamond ATR. And you can keep on the diamond, you can keep a powder sample, a liquid sample, or even a packaging material or a yarn or anything you can keep. And the amount of sample that is required is hardly 2 or 3 milligram powder sample. And the liquid sample, hardly a tiny drop of the liquid sample. That's all what is required. So this is a caffeine powder. You can get a absolutely brilliant spectrum, and in less than a minute's time. And it's very easy. There are no hassles, nothing, no sample preparation, nothing. Direct keeping the sample and record the spectrum. This is an identification of pharmaceutical excipient by ATR. Say structural formula of say hypromellose acetate succinate is a excipient which is coming in many of the pharmaceutical formulations. And Japanese Pharmacopoeia and US National NF also discuss spectrophotometric methods using FTIR, ATR methods for the identification of this excipient, hypromellose acetate succinate. The structure is shown, and this is a spectrum, and you can easily record it, and then you can compare the spectrum, and then you can identify spectrum of hypromellose succinate, acetate succinate taken with IR spirit. That's a model, what our model. So it's as per pharmacopoeial requirement. Analysis of contaminant on tablet surface by ATR. I told you, suppose you are having a pharmaceutical tablet, and if there's a stain that is appearing on this. Okay, now it is circled with a red circle. We have marked the stain. We want to find out whether it is some extended impurities taking the surface, or something which is from the real tablet itself, maybe because of improper mixing while the API and the other excipients are mixing, maybe because of improper mixing, some sort of segregation. We want to find out. So what we have done is we have taken the ATR spectrum we have taken, and we have focused we have kept it on the ATR crystal, the tablet as it is, and then we record the spectrum of that particular area. So there are two possibilities. So you look at the right-hand side spectrum, TOS spectrum, the black color is the contaminant on tablet surface. We have kept that surface on the exactly on the ATR and record the spectrum of that area, and that is actually giving a black colored IR spectrum. Okay, now we have gone for a search. We have gone for a library search. The library search is giving us two possibilities. One is a green spectrum. We said possibly it can be acetyl salicylic acid. That is one search result. And we are also getting one more search result, that is a red colored one. It could be maybe because it's also acetaminophen. So there are only two possibilities. Now we have to find out what is it, whether it is acetaminophen or whether it is acetyl salicylic acid. So what we have done, we have scraped using a small blade or something. We have scraped off that area, that patch, the yellow colored patch, and then again record the spectrum on ATR, and that shows the again on the left hand side, bottom left hand side spectra. You can see the black colored is the contaminant portion, and the library says show that it is acetaminophen. Okay, and then what we did one more experiment. The normal part of the tablet, from the other where there is no stain, the actual part, again we scraped a little material and record the spectrum, and that was identified as acetyl salicylic acid. So without any problem, we could identify the material. The supposed to be a contaminant, it is not a contaminant. It's actually one of the material in the tablet formulation itself. Maybe because it was maybe because of improper mixing or something. Something has gone, segregation has come on the surface. It is nothing but acetaminophen. It is not an external impurity. It is a very easy analysis. It's an analysis of contaminant on tablet surface by ATR. So we are confirming whether it is an external contaminant or whether it is an internal material. So it was found to be an internal material. So that's confirmed. So very, very easy analysis. Right. Then we are coming to diffuse reflectance measurement. That is another accessory DRS method. But this is normally used only for powder material. ATR can be used for powder material, liquid material, packaging films, lot of other things. But diffuse reflectance, DRS, diffuse reflectance spectroscopy attachment, and this is mainly recommended for powder material. So DRS method is applicable to almost all samples that can be pulverized. So normally here also, you have to mix the sample, around 1 to 2 milligram of sample with potassium bromide, and the mixture can be directly taken in a very small sample cup, and the sample cup can be kept inside this attachment, and the attachment will go in the sample compartment of your FTIR, and you can record the spectrum. Sample preparation is very, very easy. Okay. So DRS method is very easy to perform compared to your potassium bromide pelletization method. So it is one of the recommended USP recommended accessory for the measurement of powder samples. Okay. And diffuse reflectance, yesterday I told you what is the difference between specular reflectance and diffuse reflectance. Yesterday when we were having a discussion on UV. Diffuse reflectance means the light will go inside, and basically your surface is a structured surface, the powder material is an uneven surface. Diffuse reflectance, rough surface, diffuse reflectance will take place. The light will go inside, and when it comes out in all direction. That's called a diffuse reflectance this thing. And once you record the spectrum of your sample using a DRS attachment, here also you have to apply mathematical conversion, which is known as Kubel-Kalman conversion, KM conversion. Again, it is to apply to the software. It's a part of the standard feature of the software. And when you are applying this Kuppel-Kalman conversion, it is actually converting the reflectance spectrum into a quantitative spectrum, which is very similar to the transmission spectrum. Otherwise, you are getting from DRS, you are getting a reflectance spectrum. And that should be converted into a spectrum which is almost like a normal transmitted spectrum. And that conversion is what is done by, again, a mathematical conversion, Kuppel-Kalman conversion. It's a part of the software. Okay. And specular reflectance, of course, you may not find much interest in this because it's basically suitable for coating films on resins and metals where the film thickness is more than 1 micron. If there is a coating on a metal surface, coating on a glass, and you want to study what is the type of coating, what type of a polymer coating is done, and you can use this attachment provided the coating thickness is more than 1 micron. Minimum 1 micron thickness should be there. Then you can use this attachment. And once you record the spectrum of the material using this attachment, specular reflectance attachment, here also you have to apply mathematical conversion, which is known as KK conversion, Kramer-Kronig conversion, to the software. So there's the specular reflectance attachment. The measurement depends on condition of the coating, whether the subject, whether your material is a reflective material or matte material. Thickness of the coating, as I told you, the thickness should be more than 1 micrometer. If it is less than 1 micrometer, we have a totally different accessory for that. And condition of the substrate, whether it's a metal surface or whether it's a glass surface or what type of a surface it is. And this is how the attachment and all this will sit in the sample compartment, how it looks like. And this is an example of a PVC film on resin. That's a PVC film coated on a resin material. And you are seeing two different spectra. The upper one is without the conversion factor, and the one which is the second one, the next one, the bottom spectra is the spectrum after conversion. That is after application of a Kramer-Kronig conversion, you get a proper reflectance spectrum. So these are some of the important accessories that you are using. And the last one is a FTR microscope. A microscope can be connected to FTIR, and it has got lot of applications. Possible to measure microscopic samples as small as 10 micron in size. I told an example also. I mean, as a pharmaceutical tablet, suppose if there is a very, very microscopic, a minute black spot, and you want to really find out whether it is a external impurity or what it is, you want to identify what is that material, and you cannot even scrape it down with such a small spot on the tablet. You can keep this tablet as it is on the microscope platform, and then you can focus the light on that and you can record the spectrum. It's a wonderful attachment, FTR microscope. And you can measure the sample as small as 10 microns in size. Such a minute sample you can measure, and you can magnify that many times. You can get a very meaningful spectrum. Very easy operation used to determine contaminants on electrical contact points, fiber chips, thin layer, multi-layer packaging material, especially for pharmaceutical industry and FMCG products. Polymorphism study in pharmaceutical. You must be knowing that as a pharmacy students, you know what is polymorphism. And for polymorphism study also, you have got wonderful applications of FTR microscope. Polymorphism can be studied by 3 different techniques. The number one method is X-ray crystallography, X-ray diffraction. Second one is your FTR along with a microscope you can use. And the third one is you can go for differential scanning calorimetry. It's a thermo-analytical technique. All the 3 can be used for polymorphism study in a pharmaceutical drug. So, and then we have a lot of forensic applications also for FTR. But only thing, the cost is going to be high. FTR cost is even the cost more than the cost of FTR. The microscope cost is more than the cost of FTR. It's going to be a costly affair, but it can do wonders in many industries, especially in pharmaceutical industry, FTR microscope. And a lot of applications, minimum sample size is 10 micrometer. The aperture can help to analyze only the target position. We can precisely focus the beam on the target. We have got a very tiny spot. We can focus the beam on that spot and then get the precise spectrum measurement. auto aperture and auto stage, everything will be automatically adjusted. The three different measurement methods, transmission method, reflection method, ATR method, and very less sample preparation, less time consuming, and very, very simple operation. And there are three basic modes of I'm not going on. This is an example of a multi-layer pharmaceutical packaging. Three layers are there in this packaging. But if you look at this film, you will feel it is a single film. But in reality, it is a combination of three different films pressed together. And it looks like a single film. And if you are having an FTR microscope, and you can identify all the three layers. Layer A is nothing but nylon. Layer B is polypropylene. Layer C is polyethylene. And if you want, you can even find out the thickness of each layer. What is the thickness in terms of microns? A, B, and C. That also is possible. Okay, so it has got a lot of applications. And this is silicone grease coated on the needle of a medical syringe. Something is a very minute spot, something is getting stuck to the needle, and you want to find out what it is, you can keep the needle as it is on the platform, and it was identified as silicone grease. Because any silicone, there is a Si bonding, silicon oxygen, silicon bonding, which will come somewhere around 1000 to 1100 in between. In that region, you will get a very strong absorption band because of Si bonding, and you can add it. So it was identified as a silicone grease. Okay, the last one is conclusions. Accessories. There are a lot of accessories in FTIR. They can solve your analytical problems. Accessories save time. Lot of time you can save. Like for example, if you are going for potassium bromide pellet making in pharmaceutical industry, how much time you are going to waste for a single sample? Whereas when you are using a DRS method or an ATR method, you save tremendous amount of time. So accessories can save time. Less required for sample preparation. Sample preparations are very, very less. Many times, especially in a horizontal area, you can keep the sample as it is. Practically, there is no sample preparation at all. And less time is required for training. We can train the people, the user, in a very, very short span of time. Not much training is required. And the most popular accessories are three: horizontal ATR, diffuse reflectant. The third one, I'm sorry, I have not written, but it is a diamond ATR. That also. These three are the most popular accessories: horizontal ATR, diffuse reflectance, and diamond ATR. These are the three most widely used accessories for FTIR in many other industries, including pharmaceutical. Okay. Now that is the last slide. And if anybody wants my information, I've given my email ID and my mobile number. If anybody wants, you can note in future also. If anybody wants to contact me, you can contact me either on my email ID or you can give me a call on my mobile number. With this, I will conclude this small session on FTR. I hope I was able to put across some basic information on FTIR and the probable accessories and some of the important applications and the principles of working of FTIR and the difference between these two and all. And if there are any questions, I can take it now. Over to you, sir.
Yes, sir. Yes. Very nice, sir. Today, no anybody questions to ask on the FTIR.
Okay, okay.
Very nice and very informative session, sir, today's. And
Thank you,
also,
sir.
yesterday's is also good. You have to, we are in that academic sessions in pharmacy institutes. We have
Okay,
to study about theoretical as well as we have to go to the only practically as well as book knowledge.
correct,
But
correct.
we have to give what about basic from the industry
Yeah,
and how we have to analyze the drug, how we have to analyze the samples,
correct,
and how we have to go through it the samples from this instrument.
correct,
So this instrumentation is a basically part from the industry.
correct,
We are studying to students only from the book,
correct.
analytical book, and those are these instruments. But you have
Correct.
to go through the how you have to sample goes and all the parameters you have to study of
Yeah,
these UV as well as FTIR. So I will help. I hope to all the students which is helpful for this our today's and yesterday's webinar on the basic on the topic of theoretical and experimental study for the FTIR and UV visible spectroscopy, sir.
Correct.
I will also request to you, sir. Next month we have to organize a webinar on the chromatographic techniques, sir. Also.
Yes, sir. Okay, no problem, sir. I am available. I am available. I'll be happy to do that.
On SPLC as well as ion chromatography or any type of chromatography means those students are understanding about the what about the separations.
Sir, I can do it on gas chromatography and HPLC.
Yes. Gas and HPLC we have to arrange in that next month.
Yeah,
Yes, sir.
no problem. Sir,
I hope.
I have some very small advice to students. See,
Yes.
as Dr. Patil has told very correctly, what you learn in the classroom is
Yes.
going to be totally different when you come to the industrial lab. Is there a
Yes.
lot
Very
of difference? What you study in the classroom and when you come to the industrial lab, there is going to be lot of difference. Now, these
Yes,
type of training programs, your college was you students are very fortunate enough because your college management principal, Dr. Patil sir, they have taken a lot of pains in conducting these type of programs. Basically, you have to utilize this. See, what I am
yes,
telling, what my advice to students, when you are in the college, you are taken care of by your professors and teachers. And but when you come to the industry, nobody is there to take care of you. Are your own master. So this
yes,
is an opportunity for you to understand the basics. And once you understand the basics, you can always pick up much more advanced things without any problem. And you will
yes,
face absolutely no problem when you go to the industry. But unless your basics are clear, if you are not very thorough with the basics, you will have problems when you come out of the institute, when you come out of the university, when you go to the industry, and you will face problems unless you are thorough with the basics. So these type of programs, you can take it very seriously, understand the basics, then you are thoroughly prepared. And when you go to industrial lab, you don't have to worry about anything and you can take care of yourself very well. That is a small piece of advice to students.
yes, sir. Thank you, sir. I will. I also helpful to our students to be what about the basic objective of this to our webinar
Correct,
to
correct,
understand the basic interaction of
correct.
this UV as well as FTIR spectroscopic, and
Yes,
so we have to understand the spectroscopic techniques as
yes,
well as analysis of drugs, and also to perform the qualitative as well as quantitative analysis of
correct,
these spectroscopic techniques UV as well as IR spectroscopy. So
correct.
I will thankful to him, sir, for this attending you have to accept our invitation for this
My
our
pleasure.
and yesterday's webinar. Okay, thank
It's
you,
my
sir.
pleasure, sir. My pleasure, sir. I will be available anytime you can conduct a chromatography session. I will be available for you.
Yes, sir. Yes, sir. Okay,
Okay,
sir.
sir. Thank you all the participants for being with me for last 2 days. And I wish you all the best. And again, I think with Patil sir was telling, we will meet again sometime next month for another wonderful session on chromatography. Okay,
Yes, sir.
till then, I thank
Okay.
you so much and thank you all the best. Okay,
Okay. Right now, we end now, sir. Okay.
okay. Thank you, sir.
Thank you, sir. Thank you.